Hello. In this unit, we are going to introduce some of the key ideas, key concepts, key terms um, in the language of linear algebra. Um, by the end of this unit, you should be able to understand what we mean when we talk about a scalar, a vector, and a matrix. You should be able to perform the fundamental operations of addition and multiplication involving scalars, vectors, and matrices. You should understand and be able to explain the geometric meaning or a geometric meaning of vectors and their operations. Um, you should be able to express systems of equations using the notation of matrices and vectors to express systems in a much simpler form. And you should be able to perform some abstract manipulations of expressions involving vectors and matrices. We'll start off just introducing what I call the three fundamental objects of linear algebra. Um, these are scalars, which are a single number or a variable representing a single number. As we present scalars, the way we usually present scalars, represent them, if they're not just a number, is as a lowercase letter, very often italicized when we are presenting things in a typewritten setting. So scalar variables will usually be represented, or scalar constants will be represented by things like a, t, and x. Recall that a, given that it's early in the alphabet, is likely a scalar constant. T and x are likely scalar variables. A vector is an ordered list of scalars. It's also typically represented by a lowercase letter, but distinguished from a scalar either by putting an arrow over the value like we have, or the symbol like we have here, or by using bold-faced, particularly in type. It's a lot harder to write bold on a sheet of paper, which is why the arrow notation is nice for this. And the third type is a matrix, which is a rectangular array of scalars. These are usually represented as uppercase letters, sometimes bold-faced in type, or sometimes simply italicized, sometimes underlined. That's more common in the context of handwritten work, where we might want to emphasize that that this is a matrix. These notation conventions are not absolute. You may see other standards for how things are represented. We will generally be following these guidelines. So in this first section of this unit, we're going to discuss a little bit more about what scalars are, what vectors are, what matrices are, and give you a feel for how we write them. Let's start with scalars. Scalars are really the easiest of these to understand. Most simply, they're numbers, or variables whose values are numbers. Within the context of this class, we are almost always going to be working with real numbers, and this is something that you can generally assume, that a scalar is a real number as opposed to an imaginary number or complex number, for example, unless you are specifically asked to consider a different type of number, say a subset of the reals, like integers or natural numbers. This is sufficient for the level of understanding for our class. More formally, a scalar is defined as an element of a field. A field is a mathematical set that includes a concept of addition and multiplication, and the set has to contain both the additive and multiplicative inverse of every element from that set, with the sole exception that it doesn't have to include the multiplicative inverse of 0. Right? The set of real numbers is a field, but so is the set of complex numbers, the set of all rational numbers. These are all fields. The set of natural numbers and integers are not. This is a more formal definition that goes a little bit beyond the scope of how we are going to treat things. Scalars are used to represent real-world concepts that only require a single number to do so. Things like price, distance, speed, temperature, concentration of a chemical, age. These are all things where how we refer to them in the real world is with a single number. That's how we quantify these concepts. These concepts are all represented in mathematical models by scalars. Pretty straightforward. Vectors. Vectors are often sort of defined in different ways depending on context. If you've come across vectors defined in physics, you might have heard them defined as a value that contains both a magnitude and a direction. We're going to start with a more mathematical definition, a more general definition, of which that idea is, that physical vector idea is a subset. Vectors are quite simply ordered lists of scalars, that is, ordered lists of numbers, where we group them notationally either by square brackets or by parentheses. You'll see them sometimes written horizontally. You'll sometimes see them written vertically. At a basic level, there is no real sort of distinction between these. They are all vectors in the same sort of sense. So, for example, we might write a vector of 3 terms, as shown here, using an arrow notation for the variable and parentheses to group the terms. We might represent another vector, again with the arrow notation for the symbol, but with square brackets. We might represent group the terms vertically, again with either square brackets or with parentheses. All of these ways of writing vectors, all of these ways of denoting variables or constants for vectors are also all kind of equally valid, equally well used. Although there's a diversity of ways we can write vectors, I would recommend choosing one that you are happy with and sticking with it. Right? It'll just make things easier. It'll make it easier for others to read your work, for yourself to follow your work, and so on. We usually use symbols like M or N to refer to the number of elements in a vector, or just a number itself, an integer. And we'll describe things like we'll just refer to an n vector or an n-dimensional vector, generally substituting n with an actual number where it makes sense. So if we look at the examples here, U, this vector here, has 2 elements. It's a 2 vector. X and Y both have 3 elements. They are 3 vectors. B has 4 elements. It's a 4 vector. In formal notation, you might see something written like this. U is an element of, this symbol means is an element of. This notation of R2 can be read as simply as R2, meaning the set of two-dimensional vectors or length 2 vectors with real numbers. X and Y are elements of R3, the set of length 3 vectors or 3-element vectors with real elements. B is an element of R4, the set of vectors with 4 real elements. One of the essential sort of characteristics of vectors is that the order matters. If we rearrange the order of these terms, we have a different, these elements, we have a different vector. The way we refer to a specific element is generally by using a subscript notation. So if we have a vector v, we refer to the ith element, the first, second, third element, or so on, with the notation v subscript I. So looking at x here, x subscript 1, the first element of x is 1, x subscript 2, the second element of x is 0, x sub 3, the third element of x is negative 2. B sub 4, the fourth element of vector b, 1, 2, 3, 4, is 8.1. U subscript 1, the first element of u is negative 1. U sub 2, the second element of u is 5. For vector y, elements 1 and 3 both happen to have the same value of square root of 2. So vectors, ordered list of scalars. This summarizes how we write them down. Most people don't have sort of that much difficulty wrapping their head around the idea of vectors and how to write them. We typically use vectors to represent real-world concepts that require a list of scalars. That is, that aren't well represented by simply a single number. Position in a 2- or 3-dimensional space is one of those. Velocity, which involves a speed and a direction, is another of these. These are examples that you might have seen in physics or in Calculus 3 if you've taken such courses. But other ideas in the real world are also well represented by vectors. A set of prices for a list of goods or a list of stocks. A list of concentrations of all of the components of a chemical mixture. These are also concepts that require not a single scalar, but a list of scalars where the order matters. These are typically represented in mathematical models by vectors. Often, the individual elements of a vector will represent similar concepts measured in the same units. This is the case in the examples we listed before, the positions in 3-dimensional or 2-dimensional space. Each vector represents sort of a position that might be measured in units of spatial distance. Prices for various goods, all measured in some units of value, for example, dollars, and so on. But this is not simply required or strictly required. We may, for example, describe an individual student with a vector that contains various scalars about that student, their age, their year of study, their GPA, their student ID, various things. Each of those scalars each of those entries is a scalar, but they all mean very different things. We'll be talking about geometric interpretations in a moment. We have to be a little bit careful about geometric interpretations when we have vectors like this example of a student vector, when the values are not in the same units, when they represent very different real-world concepts. Some of the geometric interpretations become a bit fuzzy. That said, geometric interpretations can help a tremendous amount in helping students understand linear algebra, both at the early stages of defining what the objects we're working with are, what they mean, but also further along in understanding how the methods we're using works and so on. So I'd like to just sort of spend a few minutes sort of discussing this in the context of vectors. Points in space, that is points on a two-dimensional or three-dimensional coordinate system, are represented by ordered pairs or triplets of numbers. And so vectors are a natural way to represent these. Points in space can be represented simply as a point. We can represent that same idea as a line segment that starts at the origin and ends at that given point. This concept can also be represented as a vector. Again, you give a sort of an example of this just to sort of help you in visualizing in a moment. Important to sort of remember that while these geometric ideas can be really, really helpful in understanding some of the rules of how we work with vectors and understanding linear algebra, remember that vectors can be much more than this. We use the idea of spatial vectors, directed line segments to help us in our understanding of how we work with vectors, but they can be many more things than just a point in space. Just as a quick example to sort of show kind of these distinct representations or these different ways of thinking about a vector, the vector as an ordered list of 1 and 3. We might think of it simply as the ordered list of numbers. We might think of it as the point that's located at x equals 1 and y equals 3 in a xy plane as represented here. Or we might think about it as the line segment that starts at the origin and moves to that point. Directed line segment, a point in space, or simply the ordered pair of numbers 1 and 3 are all ways of thinking about this same vector. All right. Now moving on to matrices. Matrices give students a little bit more trouble at times because they're a little bit more involved, a little bit more complex in how we work with them. The simple way of thinking about a matrix and what it is that it is an ordered rectangular array of scalars or of numbers. We usually group these either using square brackets or parentheses. I tend to use square brackets, but parentheses are also fairly commonly used. And so we might write down sort of matrices that look like this. The matrix A, as in this case, is a rectangular array with 2 rows and 2 columns. This matrix V is a rectangular array with 3 rows and 3 columns. A and V have the same number of rows and columns, but this is not required for matrices in general. The matrix U has 2 rows and 4 columns. The matrix M has 3 rows and 2 columns. We generally refer to matrices as M by N matrices, either with the word by written or using a multiplication sign to represent, or a cross sign to represent by. We always write the number of rows first. So an M by N matrix means there are M rows and N matrices. A is a 2 by 2 matrices, 2 rows and 2 columns. V is a 3 by 3 matrix, 3 rows and 3 columns. U is a 2 by 3, a 2 by 4. I will correct this in the slides I post. And I will make a quick correction right there. 2 by 4 matrix having 2 rows and 4 columns, and M is a 3 by 2 matrix with 3 rows and 2 columns. It is important to internalize this rule. We always write rows first, then columns second. This is really an absolute notation that is always used. If we didn't have this rigor in ensuring that we always refer to rows first and then columns, there would be ambiguity in how we refer to a specific element of a matrix. Just as we use subscripts to denote a specific element in vectors, we do the same with matrices. We use the notation A sub ij to refer to the ith row and jth column in a matrix. So A11 is the element in the first row and first column. That is 1. A12, rows always come first, is the first element in the first row and the second column. First row, second column is 0. A21, rows come first, is the element in the second row and first column, or -1, and A22 is the element in the second row and second column, or 1. V22 is the element from the second row and second column of V, or -1. U12 is the entry in the element in the first row and second column, or -0.2. U23 is the element in the second row and third column, or 2.1. We can express the idea that all of the entries in the first column of M are the same, the square root of 3, by writing something like M11, first row, first column, equals M22, second row, first column, equals M31, third row, first column, which all equal square root of 3. Matrices are used to represent a number of different real-world concepts. We'll explore more of these through class. They can be used to represent the coefficients in a linear system of equations. They can be used to represent a physical or optical transformation. They can be used to represent a network or a graph. They can be used to represent the partial derivatives of a function. They can be used to represent covariances in a data set. And depending on the context of the problem, the the meaning of the matrices we work with will be slightly different. The tools we develop to work with them, however, will be applicable to all of these different concepts represented by matrices. Okay. In the next video, we will start exploring some of the ways we can work with these mathematical objects, defining concepts of addition and scalar multiplication. Thank you and goodbye.